Thank you. It's a pleasure to be here. So, 90% of readers of the journal Nature believe that there is a reproducibility crisis, slight or significant, or at least they did so in 2016. So since many people here, I'm sure, read the journal Nature, how many people here think that there is a slight or significant crisis? Raise your hands, just by show of hands. All right, this is actually more than I expected. We're still about 80 maybe percent, not 90, but still pretty impressive. Okay, so as I pointed out before, and I'll keep doing so, I see, from my light, there is a contradiction between this belief and the kind of evidence that we have about reproducibility. These are perhaps not all, but certainly the most influential and better conducted studies that aim to assess the reproducibility of a sample of papers, and they give ranges of successfully replicated studies that you see in no case except one or below 50%, and in all cases have an upper boundary that is well within the 60 or 70% mark. So we'll come back to this. But first, another question. Do we understand publication bias correctly? I think most people would see the problem of publication bias and the file drawer problem the same way this cartoon depicts it. So the idea is that we have journals that are fundamentally, for a variety of reasons, rejecting null and negative results, and so authors have no incentive to publish them, and so we are losing this wealth of information. By show of hands, how many people would sort of more or less agree with this picture of the problem? Okay, few, but I would say still about 50%. Good, because then I would like again to submit some evidence that made me change my mind about this issue, which is several journals of negative results have been attempted precisely under the assumption that they would have been a huge commercial success. And by the way, some of the, in fact, I think a fair proportion of these has already shut down, and in 10, 15 years of activity, you see the most prolific one published, is this how it works? 200 articles in total. And this actually now, this was the most prominent one, has shut down as well. So what's going on here? Okay, these are two examples that, to me, show that we're not really understanding these problems as well as we think we do. And what I believe is part of the problem is that we lack a proper language to talk about science on the one hand, but also accounting for the diversity of disciplines that make science what it is. And what I'm here to do fundamentally is to promote the solution that I think there is to this problem, or at least the way that I think about these problems and I find helpful, which is K-theory. And I aim to show two examples as to how, with this approach, one can study and predict even reproducibility, as well as understand publication bias more effectively. So K-theory is a theory and methodology to quantify knowledge. And it is all based on this function, which I call the K function, where K, of course, stands for knowledge. And it's a function about information functions. So whenever you see a logarithm, where am I? Oops. Whenever you see a logarithm of a probability, that effectively is a quantity of information. And if you're not familiar with the concept, a pretty accurate way to think about it is in terms of questions or answers to questions. So a certain number of bits of something is effectively the minimum number of binary questions you would have to ask to guess the value of some random variable or whatever other answer you're wishing to have. So what K-theory fundamentally says is that knowledge, what we call knowledge, is a system-specific property whose quantity is determined by how much information we wish to have about what we might call an explanandum, how much information we need to put in to obtain this new information, and that's our explanants, and how much information we will still not have, and you might call this our residual ignorance. And this is simply the mathematical translation of two postulates about what knowledge is. If we accept the fact that information is finite, that means that in order to understand the world, what we are really always doing is chunking the world into a finite number of categories, and that whatever we call knowledge is about identifying patterns between these categories, and so in a certain sense it's about compressing information, allowing us to navigate the world better, then you come up with this as the quantity of knowledge. And effectively, this translates mathematically what is a pretty old philosophical idea expressed by the early physicists and philosophers of the early 20th century, which in my opinion were right about knowledge. And all we're doing here really is expressing this idea into the modern language of classic and algorithmic information theory. And this also gives a physical interpretation to K, and a possible derivation of this physical interpretation as the number of bits of knowledge that we gain from a study, a theory, a field. Another way to understand K is to think about it in terms of a more sophisticated measure of effect size, or at least in certain uses and contexts, this is what it can be seen as, because effectively it can be translated, it's transformed rather, into, from any sort of given measure of effect size. So in this case, for example, you see how it relates to Cohen's D, but you also see how there are several functions here, because K will have different values relative to a given value of D, depending on other factors that the function computes that are relevant to knowledge from a theoretical point of view that ordinary measures of effect size don't compute. Where the methodology part of this idea comes in is that we need to define what it is the system about, the knowledge of which we are trying to quantify in order to then quantify it. So what I'll show you next, and this refers to the data that I'll show you later on, is how we would quantify K for experiments, particular behavioral experiments, but randomized controlled trials would apply as well. So first of all, we can start by simplifying a few terms and notice that this NY term is just going to be the sample size of a study. This H of X, which is what I call the input, in this case becomes the randomization in treatments and control. If we assume that it's 50-50, then that's giving us exactly 1 bit. And so consequently, the explanandum is also quantifiable as 1 bit, because the maximum amount of information that I could extract from whatever outcome I have is one in which the two groups are completely segregated, and that's just 1 bit. We can calculate the residual ignorance by transforming sort of measures of effect size given in studies, but we can also do something equally interesting, which is look at the rate of prediction failure, or success, arguably, in quantifying how much information is needed to go from our predictions to sort of observations made. And finally, we want to be able to quantify the theory and methodology underlying a study. Okay? And there is a way to do this that I've been elaborating particularly recently, and this is partly still work in progress, but it's actually surprisingly simple, which consists in translating the description, the minimum deemed necessary description of a theory and the methodology underlying a study into a graph. So each of the nodes that you see here in this graph corresponds to either a condition required by the experiment or a passage in the protocol or an element of the theory. And these are sort of in a classic way to represent these kind of graphs, a circle. And then the edges or relations between these of various kinds. And the bottom line is that once we have a graph, we have a mathematical object of which the total information we can easily calculate. And this is how we get the value of tau, which seems to be the most esoteric term in the equation, but actually, again, it's surprisingly straightforward to calculate. So, back to the first question. Why do we say there is a reproducibility crisis, given that the most prominent studies on the matter suggested that reproducibility is well above 50%? Well, to be fair to people who think in this way, there is a substantial lack of consensus in the literature around very foundational matters surrounding this whole literature. Starting with the fact that we don't really know how much reproducibility we should expect in the first place. There are various sort of opinions and models expressed about it. But fundamentally, fair enough, if you think that reproducibility should be 100% in these studies, or 90%, or some very high number, then these numbers are going to be disappointing, and you will say that there is a crisis. But we don't really know if you would be correct in making that prediction. And at an even more basic level, there is quite some controversy around exactly how we're supposed to measure reproducibility. You will notice how these studies give a range of percentages, because presently they simply use different methods to quantify reproducibility. So you get different values depending on the approach used. And what's even worse is that all of these approaches are based on rather arbitrary criteria. Okay, typically these percentages are how many replication studies passed, the p0.05 threshold or some other sort of binary criterion, which first of all is based on a statistical logic that most meta-researchers, and I'm sure many people in this audience would criticize. But it also seems to express a flawed way of thinking, and prominent statisticians have pointed this out, that it's actually incorrect to think in terms of reproducibility failures or successes. It's not a binary phenomenon, and we see this to some extent in the data. And at sort of an even deeper level, there is quite some controversy around exactly what's the point of these studies, or at least in some cases. All we seem to be doing is measuring the specific finding and trying to repeat the exact same experiment, even though in many cases what's really relevant about a particular finding is the underlying theory and the concept. And so perhaps that's what we should be focusing on more. So how do we go about understanding these problems in terms of K-theory? So our core difference is that, contrary to what statisticians would typically go about modeling reproducibility, we're not going to assume that the original study is a random draw from a population of estimates that are capturing a true underlying effect. But rather, it's a rather improbable informational structure that decoded a signal and is reporting the conditions and everything that led to the detection of a signal. And amongst other things, this means that by definition, it was more likely to happen, to be generated under favorable conditions. So for example, some finding is more likely to be reported in a population where that particular pattern is very strong. And similarly, the people who report the finding are not random people, or people that, first of all, were working on that population and probably for a long time, and they started with anecdotal observations and built up towards the finding, and they have a wealth of knowledge and expertise that might be tacit. They're not even aware of what they're doing right. Which means that when we try to replicate a study, we're always working with partial information, and so it is almost inevitable that random divergences will enter the system. Or in other words, noise enters our system and our ability to detect the signal. So this is sort of maybe the theoretical reasoning, and then there's a way, by playing around with the K function, that you get the mathematical answer, which is this function here. All this is saying is that relative to the K value of some original study, the K of the replication study is going to decline with this negative exponential function on the average, relative to the number of random divergences that indeed make the two studies different for any possible aspect of the system, and with a speed that is given by this lambda factor, okay, how rapidly one loses information. So first of all, notice how this solves some of those theoretical issues, because we, from the very start, forget about thinking about reproducibility in binary terms. In fact, we're going to start with the very assumption, if you like, that irreproducibility is a matter of how divergent any two systems are, which leads to a first broader prediction, which is simply that reproducibility, all else equal, should never be 100% really. There is always going to be divergences in at least most of the vast majority of systems. So with this very same idea, still starting from this equation, we can derive what I argue is the metric of reproducibility, which is a simple transformation of the function. So we get this uppercase lambda, which is non-arbitrary, it's not based on p-values or anything like that. It's on a universal scale from minus to plus infinity, and can be derived from any measure of effect size, I would argue any possible study. Can be estimated with very ordinary methods of linear regression, maximum likelihood, and it, in fact, physically and sort of meaningfully, substantively interpretable as a measure of information loss. And indeed, with a simple back transformation, we can get an actual proportion, which is very much analogous to the percentages that studies currently give, but that now has a meaning and is not based on some binary criterion. So what you see here are the values for some of the sort of those reproducibility studies I showed before. These in particular are studies on behavioral experiments. And you might notice how there is one group, which is the subset of the reproducibility initiative in psychology on social psychology, that has the lowest rate of reproducibility. And it's followed by another study who looked at social experiments published in Nature and Science. So, these are preliminary results. They are unpublished, but in preparation, okay? So assuming I'm right about this, then we're already detecting a pattern that basically, you know, the old approach to looking at this data would not really have shown, which is that social studies have lower reproducibility. Arguably, I would say, because they're dealing with a more complex system. And we can do more, because as I mentioned before, we can measure, for example, the predictive success of studies. And so in this case, what we can calculate is what we might call the predictive K, so a variant of K, on registered replication reports, which are studies that take one original study and have multiple labs replicating them. So this is the kind of data we come up with. So these are 7 studies, but multiple, in some cases, sort of sub-studies that had different outcomes to measure. The first bar that you see on the left-hand side of each sub-panel is the original study. Then the blue bars are really the important ones, because those are the replications. And you'll see how, in most cases, eventually we get to values that are negative, that are below the 0 line here. And that's because these studies obtained results that were in the opposite direction to what was predicted. So it's a measure of our ignorance. But overall, then, we can sort of aggregate these values into what is not quite an average, but something similar. And indeed, we can aggregate these values, not just in this way, but even taking into account the multiple dimensions along which some of these studies were tested, and get an overall value that can be either based on assumptions about the distribution of errors, or non-parametric, which basically is looking or deriving an information value by how many studies sort of were concordant with the original result rather than not. And we get pretty similar results with slightly different values. And again, we can aggregate these into that green bar and get an estimate of the total predictive K for, again, at least these 7 social psychology studies that were tested. And the answer we get is that we have about a 5% of a bit of knowledge suggested by these studies, or 15%, in the non-parametric measured. I still don't know how this compares to other phenomena. The only other phenomena I've looked at, which is in the paper that I'll mention later on, pertains to gender differences in personality, and lots of data that is available on that. And that would suggest that there is about a 24% of a bit difference. So here we would be lower, but we are averaging between a study that is, as you see, very strong in its result and others that were actually weaker. And we can do more still, because this same approach can be expanded into, as I mentioned, basically a linear regression model that allows us to explore and understand the causes of irreproducibility. So what we do here is simply derive explicitly a series of measurable divergences. And this is the result of a multiple regression analysis, which rather conservatively assumed a random intercept and slope across these 7 registered replication reports. And these are the estimates of the lambdas for the distance in years between original and replication, the difference in means between the control groups of the 2 studies, whether the 2 studies were done in the same country or not, and whether they were using similar types of populations or different, effectively students or not. The thing to notice here is that all these lambdas are negative, which is exactly what K-theory would predict, that whatever random divergence one introduces, the value one obtains, all else equal, is about a degradation of the signal. And with these values then, we can make actual predictions about how much reproducibility to expect. Because we started knowing it theoretically, and now we can show empirically that it's going to depend on the divergences, which to some extent we can measure. And so what I did next, just as a sort of proof of concept, is that I took the data from social psychology, the ones that had the lowest possible reproducibility, well, lowest measured reproducibility. And in the upper panel here, you see the naive prediction, where we're simply using the K value of the original study to try to predict what the K of the replication would be. And the cloud of points is well below what we would expect. But if we now fit those estimates of lambdas that we had before, and therefore measured a specific prediction for each of these studies, then the cloud of points comes quite much closer to the line. And notice how nice and linear it looks along most of it. And the fit overall, this is the residual sum of squares, increased by about a third, okay, with just 4 factors. All right, so this for what concerns reproducibility. Now, very quickly, the question about publication bias. Should we publish all negative results? Okay, if we understand publication bias in this way, the answer is typically yes, but we showed how in practice that didn't seem to pan out as an idea. And indeed, there is some controversy in the literature around publishing all negative results is really a good idea. Studies that pretty much start and finish with the same ideas and methods reach completely opposite conclusions, because some argue that actually, aside from the side, or rather alternatively or complementarily, I don't know, to the file drawer effect, there is a cluttered office effect we should always be concerned about, which is if we have lots and lots of meaningless negative results hanging around our office, let alone those lying in the file drawer, then it's harder for us to spot the real and meaningful information for us. And so it's going to stifle progress. So who's right? With K-theory, we can work out an answer, a theoretical answer, to a question such as what is the value of null or negative results. And we come up with the answer, which is an upper threshold of this kind, where this cardinality of t that you see here basically is the number of assumptions, experimental conditions, alternative hypotheses, alternative explanations that are, in the case of the denominator, not controlled for or ruled out by the experiment itself. And this is what the function looks like. Okay, so this is how this value changes as we increase this number t. And so you see it's a very fast declining function. Why is this useful? Apart from the fact that I think in the future one could actually measure this factor as well. But on a theoretical level, it gives a rationale to understanding where the file drawer effect should be more of a concern than the cluttered office problem, or the other way around. Because effectively, of course, when results are very valuable, negative results are very valuable, that's where we want all negative results to be published, but not in other conditions. And this is likely to map onto all sorts of characteristics, really, of studies, starting with the subject matter. Quite plausibly, physical and chemical experiments are of the former type, whereas social, ecological studies of the latter. But perhaps more relevant to people in this audience, randomized controlled trials are going to be of the former kind. And it may be no coincidence, in fact, that concerns for publication bias have the longest history in clinical medicine. And this sort of validates all the efforts and attention that has been paid to this problem in this space. But elsewhere, the concerns might be of other kinds. And this is really the bottom line, that publication bias, as well as solutions that we want to devise, are going to have field-specific costs and benefits that we can understand, at least to some extent, and at any rate, we should keep in mind when implementing them and thinking about them. So, in conclusion, I tried to convey the sense that we don't, in my opinion, understand these problems nearly as well as we think we do. And I think in particular, the problem at the core lies in the fact that we want to talk about science. We know that science is a phenomenon to be studied as a whole, but yet it's sort of fractally diverse, okay? And we don't really have a language or a framework to keep the two levels in mind when we handle these problems. And of course, mine was a shameless promotion of what I deem to be the right way to go, which is K-theory. And as I mentioned, much of what I showed, in fact, is not published in the paper where I present these ideas, but many other sort of possible solutions to meta-scientific problems are suggested there as examples, and you're warmly invited to go and download the paper. It's very modular, and you can see a little bit more what it's about. And this, to me, inspires a vision for where I would see meta-science moving forward towards a scientific understanding of knowledge. We should move from measuring the average reproducibility. I think we've done that. We've got some interesting data. Now we should do something else, which, in my opinion, consists in actually sort of experimentally quantifying the impact that certain divergences are going to have on certain kinds of studies. We measure the lambdas of those deltas, or Ds, rather. And if anything, we should do this because this would allow us then to make informed predictions or forecasts, perhaps, as to how a particular finding is going to translate or replicate in other contexts and in other conditions. Or, again, perhaps more relevant to the kind of work that many people at this conference do, we could move, or rather build upon the idea of reporting guidelines in creating a genuine taxonomy and ontology, not even just of methodologies, but of components of methodologies. And this would allow us not just to quantify K and sort of understand more about the dynamics of knowledge, but even allow, in principle, a tau calculus, where we can start to sort of play around with these ideas and methodologies in a way that would be very interesting and I think exciting. And so ultimately, these and similar sort of approaches is what could bring us from a sort of fixing science kind of narrative that I've said many times I think is misguided, to having actual interventions and policies that are tailored to the needs of specific fields, or something that, in analogy to what we say in terms of medicine moving towards personalized medicine, I would call contextualized meta-science. And with this, I'll thank you for the attention and look forward to your questions. Thank you very much.
Okay, thank you. You were well in time, so we have plenty of time for a couple of questions. Yes, Judith? I've seen you, Uli.
Thank you for your interesting talk. My name is Judith Tescheur. I work as a statistician in Amsterdam. I like K-theory, so you've got me convinced on that, but I'm not yet convinced by all your conclusions. I was mainly wondering how well are we actually already measuring reproducibility if we don't reproduce so many negative studies? Because we mainly select for interesting studies to replicate and not the disappointing ones. So is that maybe still also some data missing in your theory, or do you have that covered?
So you would want to see more negative or null results replicated to see if actually somewhere else they work.
Yeah.
That is an interesting suggestion. It brings to mind one of these many labs studies where they tried to replicate papers that were not yet published. And the interesting bit was that all of those replicated, but the only ones that didn't replicate were the total null results that actually, when replicated by other labs, worked. And so there could be interesting surprises there as well. That said, based on this kind of reasoning, I would still predict that in most cases they shouldn't work, because it just as it is unlikely in the first place to detect a signal, it's even less likely that you would start from a null signal and magically sort of be so lucky as to detect one. So my prediction would still be that in most cases we would successfully replicate the null result.
Okay, up there, and then Uli.
Test, okay. All right, thanks very much for the talk. I'm Hugh Desmond from K Leuven. So towards the scientific understanding of knowledge, as a philosopher of science, I'm kind of very interested to see how all of these problems are leading back to fundamental problems that philosophers of science have dealt with for a long time. And so I have two questions, one short one and one more fundamental. Kitcher's unification theory of scientific explanation. The K-theory reminds me very much of that, of how scientific explanation is fundamentally something of unification, and I was just wondering how you situate K-theory with regards to Kitcher, or whether that you can't keep everything into consideration, of course, so it's okay to ignore some things. And then perhaps more fundamentally, knowledge as information compression, right? So here's, a request for clarification, or perhaps it's a challenge. Marxism, Freudianism, of course, theories that were notoriously well known for information compression. Everything was explainable by sex drives or class struggles. Well, you see where I'm going with the question. So obviously, that's something that you would not want to count as valuable scientific knowledge. And so how precisely does K-theory deal with examples as those?
Sure,
Thanks.
2 quick answers to
If I
two
can
good
ask
questions.
for a not too exhaustive answer
I said
to
2
this
quick
very
answers.
exhaustive, yes.
Yeah, exactly. So, first of all, I started to think about these problems philosophically before I started to think about them mathematically. And so, as I mentioned, this is a translation in mathematical terms of philosophical concepts. So without sort of discussing Kitcher or anyone else, definitely that's where it starts from. K-theory, please download the paper. As a philosopher, I'd be excited to hear what you think about it. Offers a mathematical answer to the demarcation problem. And so it will tell you there what would show possibly and very likely Marxism or Freudianism to be pseudosciences.
Okay, so it was that short. I'll allow one more question. Uli.
There was a very insistent
Uli,
question.
it's your turn.
Yes.
It was shorter than I thought.
Okay. What I don't understand is how can you do all those calculations without featuring in the prior probability of the initially tested hypothesis? Because this is, I mean, the replication is usually on exploration. Exploration is in the totally unknown. So theories will be unlikely to be true. And if you have a very low prior probability of the hypothesis, you will end up with lots of false positives, which then in larger experiments will not replicate. How can you do these calculations without featuring this in? And I wouldn't know how to do it because we don't know what the prior probability of the hypothesis is, but somehow it must be in there.
I'm moving beyond the binary kind of thinking that you're thinking about. That said, in terms of the priors, they can definitely enter into the calculation. The key way to think about K is that it's always going to give you a measure that is sort of conditioned. And so it's in relative terms. Just like whenever you say probability, there is no absolute probability about anything. It is always conditioned on assumptions you're making. So that's where you would, the kind of conundrum you're thinking about would be solved. And you're touching on a key point, however, with regards to the prior probabilities and the false positive rate. All this thinking and this argument that most published results or false, etc., is born out of the assumption that most hypotheses we're testing is false, which I would argue is true in some fields for sure, certainly in epidemiology, but it's actually not so true in other fields where in fact people are working towards formulating the right hypothesis long before they end up testing them. And so that's why, for example, we find contradictory evidence to our assumptions.
Okay, thank you very much. Thank Dan again, and don't run away, there's a present here. Thank you very much for coming, and thank you for the nice talk. Okay, so we have